So first of all, thank you for the introduction and thank you for giving me the opportunity to speak here at this Winter Workshop. And today I want to talk about work I have been doing in collaboration with some colleagues at the University of Groningen, Ivan Kolar and Anupam Mazumdar, about the junction conditions in non-local gravity. I'm going to avoid saying infinite derivatives because people tend to go away the moment I say that. But I will explain how the introduction of infinite derivatives in the action leads to non-locality. So you already know a lot about the junction conditions because you have heard Joa's talk in the morning. It was a really nice talk, and I'm thankful for him because it makes my life a lot easier because now you're familiarized with the topic. But let me summarize a little bit the fundamentals of the junction conditions. That it's basically when you have two spacetimes that share a common codimension 1 hypersurface, and you want to know the conditions at the hypersurface in order to have a nice matching. Let's say you can describe this whole situation by a unique spacetime and a unique metric, and that your theory doesn't do any weird stuff, let's say. So basically the main objects that are going to play a role at the spacetime at one side of the hypersurface and the spacetime at the other side of the hypersurface. Then you have the hypersurface that we assume it to be time-like, the normal to that hypersurface. And then there are two interesting properties of this hypersurface. There are the induced metric at that hypersurface, that is basically the induced metric from one side, from G minus, and the induced metric from the other side. And the other one is the string-shape curvature, or second fundamental form, that gives you, some properties of the hypersurface and is related with the covariant derivative of this normal vector. Then you will see in the PDF that I'm going to share in a moment that I use these brackets. That means the jump across this hypersurface, like the quantity on this side of the hypersurface minus the quantity on the other side of the hypersurface. So basically, there are two studies that you can make with these junction conditions. First, you need to make sure that your theory is well defined in a distributional sense. Let's see, because if you now have here a surface of discontinuity, that means that you have your quantities defined here in this region of the spacetime, M minus, and you have your quantities defined in M plus. So this can be defined, as Joao said, by a distribution, the heaviside distribution, so that the quantity collapse on the value on M minus here and collapse the value plus here. And you also allow a delta term supported on the hypersurface that accounts for the effect that the hypersurface can have on these quantities. So for example, in GR, what you need to assume is just that the induced metric have the same value on one side of the hypersurface and on the other side of the hypersurface. And the fact that the induced metric is continuous, that means that there is at least one coordinate system in which you can describe this whole system by a unique metric, a four-dimensional metric or n-dimensional metric, depending on the dimension of your spacetime, that is continuous along the whole spacetime. Because Adrian was asking this morning that sometimes you impose the continuity of the whole metric, and other times you impose only the continuity of the induced metric. I mean, they are equivalent. If the induced metric is continuous, you are certain that you can have a coordinate system in which the metric of the whole spacetime is going to be continuous. And then we have seen also that usually it is imposed also in general relativity, the jump of extrinsic curvature is 0. But this is not really a junction condition, as we have seen. This is related with the existence or not of thin shells. What you obtain in general relativity is that if you have a jump of the extrinsic curvature, then you're going to have thin shells. So if you want to avoid thin shells, you need to impose that the jump of the extrinsic curvature is 0. So now, I said that I want to focus on non-local theories of gravity. So we need to see first if our theory or action is well defined and our field equations are also well defined. So for that, let me introduce first this non-local theory of gravity that I'm going to assume it to be this one, that it's basically R plus R f of box R. Basically, this f of box is a function of, well, it's an operator really, of the D'Alembertian that has infinite derivatives as defined here. I think there is a question maybe, because I hear the sound. Oh no, there is. Sorry, 1 second. Thanks you for. Oh, sorry. Well, if you have any questions, because I can see the screen, I will answer them at the end of the session. Well, basically, the fact that you have this kind of operators makes the theory non-local. And in this sense, at first I didn't see like so straightforward, like, okay, you have infinite derivatives, but why is it non-local? And the fact is that the study of the junction conditions in this non-local theory has made me understand the implications of this non-locality. Because the fact that you impose conditions on the hypersurface now is affecting the whole space-time, not just the hypersurface. Because when you have a function and you know the value of that function at the point and some derivatives, then you can see its effect locally. Like you can go by Fourier decomposition to a certain point, by Taylor expansion, sorry, not Fourier decomposition, up to a certain point. But if you know the value of that function at the point and all its derivatives, that expansion is going to give you the value of the function at every point of the spacetime. So that's when non-locality is playing a role. So let's see. Basically, well, you can do, since this D'Alembertian involves the metric, when you perform variation with respect to the metric, the field equations become quite complicated. But the thing you have to worry about is that there are some ill-defined terms in these field equations that cannot be there in a distributional sense because they are not well defined. In general, in linear distribution theory, you cannot have multiplication of distributions. So you need to avoid that in the junction conditions. For example, very simple case, f of r gravity. In r plus f of r gravity, since you have powers of r, you cannot have a singular term, this delta term that we were going to allow. For for example, like you can have the value of the Ricci scalar here, the value of the Ricci scalar here, and also some delta singular terms ported on this hypersurface. So you need to avoid that singular term in order for your f of r theory to be defined. For example, let me show you the expression of the R. You have here that the Ricci scalar in a distributional sense can be described by the Heaviside function plus a singular term that is associated with the delta on the hypersurface. And that singular term is strictly related to the trace, well, to the jump of the trace of this extrinsic curvature. So in f of r theory, one of your junction conditions is that the jump of the trace of the second fundamental form is 0. So what happens in our case is that the terms that we have here involves basically all the derivatives of R encoded in this D'Alembertian operator. Like when you analyze the field equations and also the action, you see that all these junction conditions need to, that it's basically that the jump of the trace of the second fundamental form is 0, the jump of the D'Alembertian applied to the Ricci scalar is 0 for any k, so also the jump of the Ricci scalar needs to be 0, and that the jump of the covariant derivatives of the D'Alembertian applied to the Ricci scalar, that needs to be 0 also. And in fact, that is all the conditions that you need, because now the action is well defined also if you impose these conditions. But now the interesting stuff, like how is this affecting the physics of our space-time? Like this part of the junction conditions that I speak at the beginning, like how are your field equations affected? What kind of energy and matter can you have with these junction conditions? And actually, well, via the field equations, you can study how your energy moment is going to behave. You have the energy condition and the energy momentum tensor on one side of the hypersurface, the energy momentum tensor on the other side of the hypersurface. At this singular term, the energy momentum tensor that you allow on the layer. Like for example, in Joao-like solutions, you have this thin shell that is allowed because your jump of the second fundamental form is not 0. So the kind of matter that you can have here is summarizing this 5.5 equation, that it's basically that you can have energy momentum tensor on this hypersurface as long as the jump of the second fundamental form is different from 0. And that is the same as in general relativity. The thing is that this energy momentum tensor on this layer has to be traceless. That it's something that does not happen in general relativity. Because as we know, one of the junction conditions is that the jump of the trace of the second fundamental form is 0. Then you cannot have external flux, and you cannot have this. It is called this external tension also. So we thought about these conditions, and actually this has like a very quick implications for Brainwave models, because basically in Brainwave models, let me this place, you have a bulk, let's say your whole space-time, that is separated into regions by a brane. So there you have your junction conditions. Usually, what you have is the same space-time at both sides of the brane, but with a set to symmetry. So you allow a jump of the second fundamental form, and you allow to have matter on this brain, because if not, you cannot describe what's going on in your universe. So what are the consequences of the junction conditions here? So we said that our energy momentum tensor on the layer needs to be traceless. So that would mean that the internal tension of that brain that accounts for the cosmological constant like expansion on that brain is related to the trace of the matter content on that brain. And actually, this is very interesting because there is a problem in Brainwave Models that, okay, you solve the hierarchical problem. I don't know. Yeah, and also the cosmological constant problem. But you need to impose the value of the cosmological constant on the bulk in order to have some cosmological constant on the brain. But here, the value of the cosmological constant is going to be given by the matter content in the brain. So that's something that is worth exploring. And also another consequences are star models. And I'm going to talk about two specific cases that it's basically an static star surrounded by a vanishing Ricci scalar exterior. We don't assume to be spatial, but vanishing Ricci scalar exterior. And also, I'm going to also talk about a collapsing star case. So first, for the static star, well, we need to do the matching of the metric, and you need to do the matching of the second fundamental form, because in these stars we have assumed that we don't have thin shells. So if you don't have thin shells, your jump of the second fundamental form is going to be 0. So, and for the conditions of the Ricci scalar, you have that if R plus is 0, then you perform calculations and all, and you find that the Ricci scalar, the value of the Ricci scalar and all its derivatives needs to be 0 at the hypersurface. So if that Ricci scalar is described by an analytic function, that means that the Ricci scalar needs to be 0 inside the whole interior. You know, these conditions now go beyond the hypersurface. So you can see now the non-locality playing a role in something that we all know about, that it's the junction conditions. And one interesting thing is that this constrains a lot all the possible solutions. So you cannot have basically, I think, any of the solution of the Gonzalo, Diego, and Aneta review. They are not possible in this theory if you want to have a vanishing Ricci scalar on the exterior. You cannot match them with a spatial, for example, because if your Ricci scalar is 0 on the outside, then the Ricci scalar needs to be 0 on the inside. So basically, what you end up with in the interior is like a traceless Einstein equation. And if you solve this, well, you can have a solution for the interior that can be matched with the exterior. But you need to be careful, because the corresponding solutions that you need to find have to be regular. Because if they are singular, if you say, okay, so I'm going to have sparse in the interior also, you have to be careful with that, because the fact that you have a singularity may, may complicate things in no local gravity, because that singularity doesn't only affect that point, but can affect the whole space-time. So, it's better to have regularity, and so you don't have to worry about it. The other case, it's a collapsing star, that it's basically that you define the interior to be a closed Freeman limiter of a Solvolcan metric, that it's in moving coordinates with the hypersurface. And the exterior, we assume again that it's going to be a spherically symmetric static geometry with vanishing Ricci scalar. The thing is that I have learned a lot about these collapsing stars with the junction conditions, because if you impose the continuity of this induced metric, you find that your radius, it's now dependent on the form factor, and now you can see that your spatial radius, it's depending on the value of the form factor and how it is evolving. So I think that's kind of cool that the junction conditions impose these relations that see you that you're, you realize that you're actually describing a collapsing star, that your radius is contracting if your form factor is decreasing. So basically, you assume the continuity also of the second fundamental form, and in the end, imposing also the conditions on the Ricci scalar, you arrive at the same conclusion, that all the derivatives with respect to this time in the Freeman limiter of work coordinates at the hypersurface need to be zero. So that means that the Ricci scalar in the interior must be zero. And that imposes that you can have only one possible kind of collapse. And that's huge. Like, only with the junction conditions, we have not solved the field equations yet. Like, just with the junction conditions, you know that if you want your exterior to be a vanishing Ricci scalar solution, then your interior can only have one kind of collapse. It's already very restricted. So now you can go to the field equations and see if this is a solution. But as I have said, this scale factor is singular, because it tends to, this is a singular collapse, what it's describing. So it is difficult to see if this is actually a solution of this non-local theory. But what we do know, if we want to describe, for example, a bouncing collapse, you cannot have a spatial lab an exterior solution. So yeah, that's basically it. But I want to talk about future works and on these topics. One of them is to include the quadratic Ricci tensor and the quadratic Riemann in the action to see what these impose on the junction conditions, and probably they are a lot more restrictive and probably even implying that you need to have the continuity of the metric along the whole space. I mean, the continuity of the metric and all the derivatives of the metric, which means that you can not actually glue two different spacetimes, but you need to have the same spacetime at each sides of the hypersurface. But we'll see. We're still doing some calculations on this subject. And another subject is, to study more these non-local theories of gravity, explore its stability beyond Minkowski, because we know that these kinds of theories can be made ghost-free around a specific background. But since you have functions of the D'Alembertian, which this depends on the metric, this is like, no, I cannot say strongly coupled because I have calculated it, but it depends a lot on the background that you are choosing. So probably these kind of theories has a strong coupling problem, and this is something that interesting because they are raising a lot of attention now, and if they have some unstable behavior, it's good to to calculate it now and not keep studying these theories. So thanks a lot for your attention. And if you have questions, I will be happy to answer them.
Thank you, Francisco, for your talk. It's been very, very interesting. So, are there any questions in the audience? Let's give them some time to clap, virtual claps. I can do it. So, is this paper, first of all, is this paper available on the archive?
Well, it's going to be available next week, probably.
Very good.
Because, but yeah, if you are interested, you can keep an eye on the archive, and also you can send me an email.
Yeah, very
good.
I have questions and comments.
Yeah.
So let me start. So first of all, is the idea of considering the junction conditions in with infinite derivatives is challenging. First of all, okay.
Yeah, it is.
Because if you have any discontinuity, like in GR has second order derivatives of the metric. So the metric is continuous in the junction. So you have first order discontinuities in the derivatives, so that is acceptable. But if you have more derivatives, then that discontinuity is going to give infinities. So, this is, in principle, I was very excited about what you had to say, okay, because it's really a non-trivial problem. And then it seems natural what you get is that all these the discontinuities in all these higher derivative terms should be zero. So you need highly continuous functions like the scalar curvature, and its derivatives must be continuous. Okay, so this is apparently a consistent result. Okay, it is intuitively reasonable. So, but then when you consider the explicit examples, okay, matching of exterior Schwarzschild with some interior solution. I think, in my opinion, this example is too much. Let me see. Restrictive. That's the word. It is too restrictive because I think you are missing. You could have maybe you have done it and you have considered other examples, but in my opinion, considering an external vanishing Ricci case is too restrictive to really try to get new results related to the new dynamics of the theory, not the possibility of non-local effects and infinite or higher order derivatives. Let me explain why I think it is too restrictive. Because even in theory with a finite number of box operators acting on the Ricci, okay, in those cases you can replace the boxes by new scalar fields. So you can introduce a number of scalar fields that modify the dynamics. Okay, so these scalar fields represent new degrees of freedom, and for any solution that you want to find, you need boundary conditions for those degrees of freedom, for those scalars. Okay? And those boundary conditions represent the non-locality, the non-local properties of those theories. So when you have an infinite number of derivatives, so you expect an infinite number of scalar degrees of freedom in some sense. Okay. So the point is, when you have additional scalars, then typically you get in the weak field limit Yukawa type corrections. Okay. So this means that outside of the sources, where in GR you get vanishing Ricci, in any other theory with scalars, you will have Yukawa type corrections. So those things, those corrections will be there unless you completely freeze the scalars. And so the condition of vanishing Ricci that you're imposing, or even if it is a constant Ricci, is freezing all the non-local terms, all the relevant physical properties, okay, all the new things of the theory. So So first of all, is this consistent what you said? Did I understand correctly?
Let me clarify a few things. Is that although they seem like these junction conditions seem like very intuitive, like what you would expect, like actually we need to make a lot of assumptions on these form factors, on these FO boxes, in order to obtain these results. Because the thing is that this kind of infinite derivatives operator can regularize or deregularize situations. For example, if you have a delta source, this, at least in the linear regime, this can be regularized with the infinite derivatives. Like now you don't have a delta, but this delta is smeared out by this FO box operator. And also you can have the contrary. You can have a completely smooth background, but when you introduce this kind of non-local operators, then you deregularize and produce, for example, a brain. At least these have been studied in the linearized regime. So we need to be careful and actually assume that these are FO boxes that cannot regularize or deregularize any kind of behavior. So this is restricted to some kind of form factors. And the thing is that, the examples that we have considered are very simple and very restrictive, because we are not trying to find new solutions. Like, results of this paper is basically give the junction conditions and explore a little bit its consequences, but not find new solution based on these junction conditions. Probably if we assume a more general exterior, I mean, I have calculated also, but if we assume a general spherically symmetric exterior, what you find is basically a relation between the interior P plus and Q minus with the exterior P plus and Q minus. You need to assume a certain value for these functions in order to constrain the whole interior. Like, we wanted to show how these junction conditions can go beyond the hypersurface. That's why we chose like a simple example that you can actually, see it very, very easily. And the same with the collapse. And what we obtain is basically like a no-go theorem, that if you want to describe more interesting situations, then your exterior cannot be sparse. So probably when we try to find new solutions of the theory that actually have this non-locality into account and all, it will be good to relax the Ricci scalar vanishing in the exterior. Yeah, I agree with that.
Yeah, very good. So we are in the same way. So I would recommend or encourage you to study other external configurations just to see how that is related. And not the properties of the exterior can affect the interior, because that is where the new physics of these theories is. Okay, so you want to realize real capabilities, you have to consider non-trivial solutions, and that's the challenge. So I don't have any any suggestions. So that's your homework. Okay. So any other question in the audience? Nobody? Any questions, comments, complaints? Nothing? Okay, so in that case, Francisco, thank you again for participating and for your talk.
Thanks to you.